Hey guys. I know some of you are still logging in. I was hoping to give you more notice, but I just got inspired. So here we are. I'm going to talk to you a little bit about what to expect. So, this is what I covered on Thursday's after school review session. I'm calling it geometry review number 2. The focus is pretty much transformations with constructions. Some of your classes did really great and you were able to get through all these questions and I gave you the correct answers. Some of your classes didn't hit that. So I'm just going to try to see what I can do to help you out tonight as we stream live. And then also you guys can watch it later if you don't have it. So I do have the chat open. There is a 30-second delay. Let me just stay here. I guess we'll get started. So most of you don't really care about this, so I'll just go over it again. The quote I had shared was, "It's okay to not know. It's not okay to not try." And that's really, really important. The whole premise of the growth mindset is not only that you just believe you can and that effort is good, it's that effort really matters. And it's more about the actions and the steps that you take to get where you're going. Of course, anytime that you watch any of these YouTube videos or other things to help you be successful, you should have paper in front of you. You should have a pen and pencil, perhaps a calculator or your cell phone, and ideally your EOC notebook. Coming down here, of course, our central questions are, how does demonstrating a growth mindset impact my success on the EOCT as well as the district assessment? Now, I have shared, I think with most of you, that this first 2 weeks, like up until May 2nd and 3rd, our number one focus is going to be on EOC preparation. And EOC questions are different than the district assessment questions. They're, I don't want to say lower level, but they're just perhaps some of them not as rigorous or challenging or as multi-step as the district assessment questions are. When the EOC is done, I'll give you a little bit of a freedom for a brain break. And then we're going to go right into prepping and preparing for the district assessment. And I have some questions I've already been pulling from some of the other school districts and states that I worked in, which have those multi-level questions. So whether they're on the interim or whether on their DA or not, I don't know. But at least you'll see those types of questions. But these questions here are all to help you be successful on the EOC. Now, I can utilize tools and resources to positively impact my performance on assessments. And also working collaboratively with others so that you can learn and grow with your peers, hence the chat box. Again, the chat box has a 30-second delay, which is a little bit of a bummer. Other goals are, how do objects relate in two-dimensional space, and really identifying and conducting our transformations, and then using rotational symmetry, which I cannot guarantee anything. I haven't looked at the test or anything, but I can tell you rotational symmetry comes up a lot when I look at what's called the AKS, which is things that you should know. And so we're going to make sure that you have an understanding of that. We're also going to be taking a look at interpreting different types of constructions. So first things first, what are transformations? Well, transformations are any way that describes how a shape moves. Now, there's 4 main transformations. 3 of them, which are the 3 on the screen, deal with something called rigid motion. And let me type that lovely thing out, rigid motion. And if you came to my training, or perhaps I shared it in class, I might have said something like, okay, I'm looking at you in a camera. It's being reflected. I'm still Miss Eric. I haven't gotten bigger. I haven't gotten smaller. I've just moved in the space. If I slide to the left or slide to the right, I'm still Miss Eric. I'm 100% me. I haven't gained anything. I haven't lost anything. If I rotate in my chair, I'm still Miss Erig. Nothing has changed. Those three types of motion are called rigid motion. And basically, rigid motion means that everything stays congruent. Repeat after me. Everything stays congruent. I can't hear you, but that's really important to know. So after these moves, it's still the same size, same area, same line lengths. Everything stays the same. It might be pointed up and then it's rotated pointing a different way, but no matter what, the points will still match up. The size will be the same. The area will be the same. The lines lengths will be the same. Now, let's look at a couple examples of that. Woo, we don't need that pink dotters. Okay, so reflection. Things to know about reflection. And I'm going to try to use my highlighter tool. Okay, reflection means that's awful. Flip. And specifically, think of it by like looking at yourself in a mirror. You see your reflection. Your size doesn't change. Who you are doesn't change. Basically, it just flips. That's what happens here. Now, if we draw your attention to this side of the screen, I told you that anytime you reflect over the x-axis, which goes like this, the y-axis that goes like this, or any other line. For example, if you have y equals 2, you would count up 2, and that would be y equals 2. If you have x equals 5, you'd go over 5, and then that would be your line. Well, anytime you're doing like a straight line, not like a diagonal line like y equals x or y equals negative x, but a straight line, you're going to count boxes. And that's going to be how you see do the reflection. So if we take here and we look at this point, I went 1, 2, 3, 4 over. So it's 4 straight boxes to my line of symmetry. Then I know that that's 4, so I'm going to go 4 more, 1, 2, 3, 4, and that's going to give me my new point. This is called the pre-image. This is called the image. You do the same thing again. Let's take it here. How many to the line? 2 to the line. How many from the line? 2 to the line. It's like to the right, to the right, to the left, to the left. That's what you're doing. You're counting whole boxes. The same would be true if you're moving up or down. So if you're moving perfectly left or perfectly right or perfectly up or perfectly down, you count whole boxes. Now, you absolutely can memorize this for sure. I wouldn't. I prefer to count boxes. So my EOC hack is, yeah, that's very important information. Don't pay attention to it. If you know how to count boxes, you can do the EOC hack and you'll be fine. So, and you'll get the right answer. It'll work. The only thing that might be a little tricky is when we come to this part right here, where we do the reflection of the origin. And that basically is you'd have to do a double flip, or you can just remember that the signs change. Let's take a look at the next slide. Here, it's a little bit different. In our first example up top, we were having straight lines. We were reflecting on straight lines. In this example, we're reflecting over a diagonal line. Notice the head tilt, diagonal line. So we are now going to count diagonal boxes or corner to corner. So if I start here, I said, okay, how many corners do I go to get to this line? 1 full corner and 1 half corner. So basically I know I'm going 1.5. So that means I do 1.5 diagonal to the line. So I'm going to go 1.5 diagonal from the line. 1.5, there's my half, here's my 1. I went 1.5 and that's how I got my new point. Here, 1, 2.5. 1.5, there's the half, the first half, 1.5, 2.5. So anytime it's angled, you're just going to do the diagonal. Let me model it one more time. Here is just this little beep, 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 half. One more little beep, 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 half. And that's how it moves. Okay, the same is true if the line that you had instead was like this. So here's our reflecting line like here. Okay, the same would be true if the reflecting line went this way. If it went that way, you'd count this way, how many down and how many over, and reflect. But the main thing to remember is if the initial line is diagonal, you're going to have to count diagonally. Okay. You can go back and you can be like, dude, I really like to memorize formulas. I have tons of time on my hands. You can memorize these formulas. I would not memorize the formulas. All I would remember is when I'm reflecting over a straight line up and down or a straight line left and right, all I'm going to have to do is count my boxes. Here, I'm counting 4. So then I count 4 more. Here I count 2. So then I count 2 more. Hey, Jonathan, good to see you. If you go over here on the diagonal, all you're going to remember is you count diagonal and then diagonal again. That's it. You don't have to remember everything else. That's all you needed to know. Okay, so moving on. Let's delete this slide and go on. Now that was reflections. The next topic I've got is rotations. So rotations, you might be beneficial if you memorize it. If you can, that's great. It'll help you out. If you can't, that's also okay. Basically, the things that you have to remember is if it goes across, if it's 180 degrees, the X and Y stay the same. The only thing that's different are these negatives. That's the only thing that changes. So if you can remember, okay, when I go across, my X and Y stays the exact same numbers. Those numbers don't change. The only thing that changes are the signs. So let's take an example real quick. Let's say that my point was, we'll take this point here. That's not really good. Let's say our point was 5, -2. This was our starting point. All we're going to do is, okay, first, it's easy to just like write it right out. First, switch the signs. When you switch the signs, that moves it to the 180 degrees. So this would end up becoming the opposite of +5 is -5. The opposite of -2 is +2. So that's that one. The numbers stay exactly the same for rotations of 180 degrees. The only thing that changes is the signs. And, you know, I don't know if you want to think about gravity and if you like turn something upside down, what falls out. But basically, the numbers stay in the same place. The only thing that changes are the signs. For both the rotating of 90 degrees and rotating of 270 degrees, the signs don't, or the order doesn't, the order changes. Okay, so 180, the order stays the same. For rotation of 90 degrees, the order changes. So here, it becomes -yx, and here it becomes y -x. The way that I would remember to do this is 90 to 70 flip. So right away I know, okay, I've got 2, -2, 5. And then it kind of makes sense. See here how, if this was where it was, see how it changes the y. It's still, I'm sorry, I misspoke. This is rotating counterclockwise. If we picture rotating it this way, we can see how the y would change. So this -y becomes +2/5. And that's how it kind of goes it. Same thing for the 270. We have our 2/5, it changes signs, but the y stays the same and the x becomes the opposite. I think I just made that way more confusing than it is. But moral of the story, try to remember them. I look at it by quadrants. The other thing you can do is you can hold up a piece of paper. So when you hold up a piece of paper and you apply it to your screen, you can kind of turn it and see how it goes. See, here's a little giraffe. Hi, Mr. Giraffe. All right, moving on to the next slide. Translations are probably, to me, the easiest, but some of the kids really struggle with this. All you're doing is adding or subtracting. That's it. It's not multiplication, division, or anything. It's like add and subtract. That's it. So basically, count the boxes that a point has been moved, and that's how you can determine what the translation is. This picture is a little bit funkity-dunkity, so it might be harder to count, but I could see here that this went 1, 2, 3. It went over 3. So I'm going to put x plus 3. Oops, that's supposed to be a comma. And then here's my 1, 2, 3. And then how many up? 1, 2, 3, 4. Y plus 4. That's literally the translation. Now, when you'll see translations on the EOC, you'll see them, part of it being the unit. Translations only come into play in second semester. So like, for example, on the district assessment, perhaps if you're doing something like all circles are similar. That would be an example that we use transformations this semester, where basically it's like, here's a circle. We know all circles are similar because they all have a relationship with a ratio in their diameter and radius. And here's the circle. And now it got bigger and it moved. So you would need to do a translation to see what the center is here. Here's my center. And I got bigger. So that's kind of where that comes into play. And we'll do more circle problems for sure. Okay, we're not going to play Kahoot because, you know, we're live. That would be really fun if we had a bunch of people online and we played Kahoot from like our different houses. That would be cool. Let's take an example of some of these. So here's an example of a translation. It says it wants me to subtract 3 and add 2. So first I'm going to subtract 3. Oops. And then I'm going to add 1. My mistake. So pick any point. I'm going to pick this point, even though it's not where the arrow is pointing. It's easier for me to count because it's on like a perfect point. It's at 1, 0. So I'm going to go back 3, 1, 2, 3, and then I'm going to go up 1. And here's my first point. Let's make that point black so we know it's important. Now we're going to go back and we're going to do it again. 1, 2, 3, up 1. So here's my next point. Let's turn it into black so we can see it. And then we do it for another one. This one might be good. 1, 2, 3, up 1. And then switch it over, make it bigger. And then now we've got our shape. I mean, it'll look nicer. The good news is you won't have to do this on the EOC or the district assessment because the district assessment are all multiple choice questions. And the EOC, you have to type your answer. So you're not going to be able to draw. But you'll still might have to interpret these shapes. So that's why it's important. Here comes the next one. Here it says to reflect across the x-axis. This is where some kids get confused. See this point? It's literally on the x-axis. So they're like, oh my gosh, what am I going to do? Well, nothing. It literally just stays right there. Ta-da! Congratulations, you've done that already. Now, remember reflection. I said you count boxes if it goes a straight line, horizontal or vertical. So that's 2 down. So we're going to go 2 more down. And that's going to be our new point. Hello, new point. Nice to meet you. Now, connect the dots. Let's do it again for the next one. This would be the next one. Here, 1, 2 down, 1, 2 down. Black ink. Here I get right here. Connect the box. Do it again for the last point. 1 down, 1 down. Here it is here. Connect it. And then as best as I can draw my line. Okay. Let's trash that and go to the next one. Okay, now we're reflecting across the diagonal. Remember what I said when we reflect across the diagonal line, we count the angles going down. We count the diagonals or corner to corner. So here, some people, they wrongly count down 2 and we'll count down 2 again. That's the bat. Don't do that. Angles. This line is slanted, so we're going to go on a slant. Technically, reflection is we're doing the perpendicular. So we're going perpendicular to the line. So when it's flat or like this, perpendicular are straight lines, horizontal or vertical. See how this is angled? We're drawing the perpendicular that way. So anyway, there's our one. Here comes our other one. So now we're like, yay, I found my first point. I feel amazing. Then we do it again. This one is 1.5. Here's my half. Here's my 1. Here's my point. Now, at this point, if you're secure and what like those two are correct, you don't technically have to do the rest of those because you could be like, how long is this box? 1, 2, 3, 4. So you can be like, all right, 1, 2, 3, 4. 1, 2, 3, 4. And now I've drawn it. You could go that way. 1, 2, 3.5. Here's my half. 1, 2, 3. There's my point. 1, 2, 3, 1, 2, 3. So you could have done it that way. I sometimes just get lazy and count. That's it. All right, here comes the next one. This is just rotate or reflecting it on the other way. This point stays the same. Again, we count angles. Here's 1 down. Here's my next one. So there I've got my baseline that I need. I could do the rest of them or I could count 1, 2, 3, 4. 1, 2, 3, 4. Here's my bottom. Like that. And that's it. Done. Woohoo! Trash. Next one. All right. So the next thing we're going to talk about is dilations. Dilations get things larger or smaller. They create similar figures. This is so important. Dilations have similar figures. Okay. Basically, if I lost a ton of weight and came to school 50 pounds lighter, I'd still be Miss Erig, but I'd look different. Okay. I'd be similar because I'm still the same spirit or soul person, but I'd physically look different. That's kind of what I want you to think for dilations. Rotations, reflections, translations, those same person the whole time, same size, everything. Dilations are similar. Where you're going to see this the most in our semester 2 work, we talk about circles, because like here's this beautiful circle here. Here's this beautiful bigger circle here. These circles are not congruent because they're not the same size, but they are similar. That's just like the Ricola song. Ricola. Again, this tells you down here that dilations do not preserve distance or congruency, but they are similar. And because they're similar, they are also proportional. And that's something that you should know. So if you are watching this later and you have your EOC workbook that you've created, you should write on dilations, similar, proportional, circles, all that kind of stuff. That's what you should be doing. Okay, so let's take a look. There are times where you have to create the center of dilation. And let's take the look right here. That's my lovely dog playing with her toy. How do we find the center of dilation? You find it by connecting the points. So let's take a look. Here is my D, and here's D prime. All I'm going to do is, to the best of my ability, I'm going to use a piece of paper to kind of help me. I'm going to draw a line. It might not work, but we're going to keep trying. Then I'm like, where's my E and E prime? Right here. Where's my, yeah, that definitely didn't work. Let's try that again. One more. You know what? I'm going to connect the other ones first. Here's my FF. Here's my EE. That should be enough to help me get my D. And now when I connect the D's using a straight edge, we did it right here. That's going to be the center of dilation. That center of dilation happens at 1, 2, 3, 4, 5, up 0. So basically, again, you're not going to have to draw center of dilations on a piece of paper because you won't be able to draw them on the EOC, and center of dilation is a topic from Unit 1 last semester, so it's not going to be on your district assessment. What you do need to know is there might be a question on the EOC where they give you the images and you have to maybe hold up a piece of paper on your screen, draw the shapes, and then come up with where the center of dilation will be. Let's see. I think that might have been our only, that was unhelpful. Our only dilation one. Let's take a look. No, we got another one. Okay, which transformation results in a figure that is similar to the original figure but has a greater area? In this example, I like to think of money, because area, money, you can just all you're doing is making up numbers and see what makes sense. So because this says greater area, I know that I'm talking about money, and it says greater area, I want greater money, or specifically, I want more money. So come up with a number in your head. I like 100 because it's simple. Let's switch to green because we're talking about bucks. If I have $100 and I have my calculator and I do 100 times 0.25, I get, bam, I don't know if you can see, 25. So 100 times 0.25 gives me $25. So you have to say, dude, is $25 more than $100? Oh, I don't think so. So we're going to cross it off. Now, for some of you, just seeing that, you'll know right away what the answer is. But in case you didn't, let me keep showing you. Now, let's look at this one. This says, what's 100 times 0.5? Well, I've done this problem so many times. I can tell you that half of $100 is 50 bucks. Is 50 bucks greater than 100 bucks? Nope. So we're going to cross this off. Now it gets a little bit tricky, and this is where some kids make a mistake. They're like, what's a dilation with a scale factor of 1? Dude, if it's a scale factor of 1, nothing happened. So all you're going to do is, what's 100 times 1? 100. You didn't make any money. You didn't lose any money. It's the exact same. So that's not going to help. So by process of elimination, we know that it's choice D, but let's just prove it. We have 100. We're multiplying it by scale factor of 2. So now we have $200. Is $200 more than $100? Yes. So that's why it's our answer. Anytime you see scale factor, it wants you to multiply. Now, sometimes you might be multiplying by a decimal. Sometimes you might be multiplying by a fraction, but it always means multiply. Say that. Scale factor, multiply, multiply, scale factor, multiply. Next. Okay, here's an example of a circle problem. Circle P is dilated to form circle P prime. Which statement is always true? This is a trick question. When kids see the word dilated, sometimes they think big and they think, oh, here's my pretty circle P and here's my P prime. And look, it dilated, it got bigger. But guess what? That's not always the case because dilation, it can get smaller. Your pupils can become smaller, okay? So little p prime, it could also be this one. So in this case, you have to think about both big P prime and little p prime. Both make a difference. They're both very important. So we have which is always true. So that probably means that sometimes there might be a couple that are sometimes true, but we're looking for the one that's always true. So is it always true? Now, did you notice how I just did that? Notice how I just said always true in front of it. So is it always true that the radius of circle P, so here's my radius. Let me just kind of picture it. Let's draw radii for all of these. My radius for circle P is equal to the radius of P prime. Well, that's pretty obvious that that's not the case. The only time would be if it was a dilation of 1, which I've already told you doesn't happen. So let's take that off. Goodbye. That doesn't help us out. Ooh, that was a mistake. Let's do our P's real quick. P prime, question mark. Baby P prime, question mark. Okay, so now it says the length of any chord in circle P is greater than the length of any chord in circle P prime. Well, let's see. Is that chord bigger than this chord? Nope. Let me show you again. A chord is any line that goes from two endpoints of a circle. So here it is here. Look how big that chord is. It would be true between the first circle, P, and our third circle, baby P prime. But it's not the case for circle P and big P prime. So we know we're going to cross off that. Okay. The diameter, let me just erase those yellow lines so we are back on track. The diameter of circle P is greater than the diameter of circle P prime. Again, here is our diameter of P. Oops, that wasn't helpful. Draw my circle again. Here's our circle P. So here's my diameter of circle P. Is that line bigger than this line? Right away, it's a no. It's bigger than the circle 3's line, but it's not bigger than what it could be if the P was enlarged. It became big P prime. So it can't be that one. So by process of elimination, it is D. Let's just confirm why. D says the ratio of the diameter to the circumference is the same for both circles. And dude, what's the formula for circumference of all circles? C equals pi D, or you might remember C equals 2 pi R. Is that formula the same for every single circle in the world? It is. Yes, say yes. Is that the same for every circle in the world? Yes. Okay, that's why. Okay, so the ratio of the diameter to the circumference is the same for everything. That question is done. Process of elimination. Goodbye. Okay, now sometimes you see composite transformations. And again, this will not be a topic that you should see on your district assessment because it's a unit 1 topic and your district assessment starts at circles. But it could be on your EOC. So what do you need to do? Well, anytime you see a composite, basically it means there's this little teeny circle on the inside. When you see that, you always do what comes second first. It's like you do it in reverse order. So basically this is saying like, what is the take a shape, translate it 3, -4 first. So write 3 down 4, then do the 9 degrees. Okay, that's it. So if I had like a coordinate plane here and I had a shape here, I would go over 3 down 4 first. So I'd be like 1, 2, 3. So here's my new one. Then I'd go down 4. So it'd be somewhere around here. And then I would rotate this 90 degrees. And remember, rotating it here would put it on this side. My Y's and my X change places. So it would be somewhere up here, give or take. So it would go here first with my translation of 3, -4. And then it would go this way with a rotation of 90 degrees because we do the translation first. Now, I'm not sure if you're going to see this. I haven't seen this frequently in other places, but it may be something that's important for the EOC. Basically, what it says is it says that if you have 2 reflections over parallel lines, it's the same as a translation. And if you have 2 reflections over 2 intersecting lines, it's the equivalent of a rotation. I haven't really seen a question that specifically addresses that, so I'm not going to spend time on it, but FYI, that is there. Now it says specify a sequence of transformations that will map ABCD onto PQRS in each case. So because it has a sequence, it pretty much means we're going to do more than one. So first, some kids might be like, okay, well, A has to go to P. So I'm going to write A to P, because that is just a way for me to remember. Now, technically, B has to go to Q, C has to go to R, and D has to go to S. But if you just remember that A has to go to P, you'll be able to do this a lot more easily. So how do we get this point right here down to here? That's our first thing that we have to do. Well, we could translate it for sure. We could go down over 4 and down 1. But if we did that, that would just move the rectangle like this. So that's not going to fully help us. What we could do is, you might see it already, this little guy could come down. So he'd be like beep, 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 beep. So he'd be laying down right here. And this would be where A prime would be. Then if we rotate it 90 degrees, boom, stays the same. We're basically taking the shape and turning it, it land on top, and A and P would match up. So basically what we did is we first did a translation of how many units down. I didn't even count. 1, 2, 3, 4, 5. 5 down. And then we rotated 90 degrees. Woo. For this next one, it's a little bit different. This next one, notice how this is pointing up and this is pointing down. Same thing here. This was going side to side and this one's going up to down. Because of that, we know no matter what, there has to be a rotation. That's the only way that the orientation is going to do it. You can't do it from sliding. And I guess you could technically do it from flipping. Here, it had to be a rotation. This could technically be a flip. And that's actually what we could do. One thing is, well, this one you can't rotate. If you rotated it 180 degrees from this given at this point, then your new shape would look like this. And then if you rotated it another 90 degrees, it would look like this. So you could do a rotation of... Yeah, that's probably one thing that you could do. One thing that you could do if for this one is you could rotate 180 degrees, and that would put it here. And then in order for this point to get here, we'd have to reflect it on X = 4. So that's one way that you could do this. I know I did that fast. Pause it, go back, watch it again. The other thing that I could do, which is what I was thinking about doing to begin with, is I was thinking you could reflect it on Y = 1. So these are 2 answers. When you reflect it on Y = 1, you get this shape. After you do the reflection, now you can move it 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And then you can translate it 6 units over, and you don't have to go up and down. That's another way. So either one of those translations work. Let's see. Okay. Which sequence of transformations maps triangle ABC to triangle RST? Again, let's take a look. Now, see how this is pointed up and this is pointing up? Because both are pointing up, we know it can't be a rotation, because any rotation would end up turning it and having the point either go this way, if it was 90 degrees, counterclockwise or 270 clockwise. It would have it be pointed down like this if it was 180 degrees. And it would be pointed like this if it was 90 degrees. So because none of those are the case, we know it right away. It can't be a rotation. So let's see, make sure there's no rotations. Yep, we're going to cross off C and D. It can't be a rotation. So now we're left with the next one. Well, no matter what, both says reflecting over x equals -1. So we might as well reflect over x equals -1. Here's x equals -1. Now let's do our reflection in pink. 1, 2, 1, 2. Here's my first point. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2. So now we have this. So we know that that's what it's going to look like. Now we have to see how many do we have to move this pink triangle so it's on top of that one. Well, some wrong students think, oh, I can just move it down one and now it's on top of here. Well, if you do that, that's what it's going to look like, which would be wrong. So don't do that. You need to map the entire pink triangle on top of the entire RST triangle on the bottom. So how many down would we have to go to get this point all the way down here? 1, 2, 3, 4, 5. We'd have to go down 5. Ooh, which is choice B. Yay, we did it. High five. Woohoo. All right, trash this. I did it again. Trash. Pencil. Okay, let's take a look at rotational symmetry. I guess we're going to have to stop after this because I didn't want this video to go too long. Where are we? Yeah, I think we'll just do rotational symmetry and stop there. Because, yeah, I wanted you to be able to watch it in a shorter period of time. Okay, rotational symmetry is this. Basically speaking, all you do, and this is in your book, it's right before that you take glued in these questions, is you take 360 degrees and you divide it by the number of sides. 360 divided by sides. Okay, wherever you are watching this, even if you're in the car watching this, you're going to say 360 divided by sides. Go. Don't be lazy. 360 divided by the number of sides. I can't guarantee you, but this is a consistent theme that we see in geometry. So I would expect that you would see something like this on the EOC. I might be wrong, but I would expect it. So let's take a look. I get it again. Okay, so a regular pentagon is centered and has a origin and has a vertex at 0, 4. Oh, here's the 0, 4. This is the vertex. Then it says, which transformation maps the pentagon onto itself? Well, reflection on M. Let's see. Reflection on M. Here's M. Let's count. 1, 2, 3. 1, 2, 3. So here would be 1 point. These points would stay the same. So if I was to do a reflection on M, that's just over 3, 4. So that, I mean, I hope we can tell right now that those two shapes don't look the same. The reflection just doesn't make sense. We're going to cross out A. And then now we're going to cross out A. A reflection across the x-axis. Now, if it's at a reflection across the y-axis, that would be true because this would go here, this would go here. So if it was the y-axis, then it would be yes. But that's not a choice. The x-axis basically is, I'm going to put a different color across this line. So if we reflected it this way, it's pretty much going to give us the same thing that we saw with M, but just drop down. So let's just agree to cross it out. So now we're at a rotation. Now, not every time you will see questions where it's not the case, but most times if you see the word itself, it wants you to do rotational symmetry. So again, remember what I had you repeat, 360 divided by the number of sides. In this case, you have 5 sides. So I'm doing 360 divided by 5. I've done this problem enough to tell you it's 72 degrees. OMG, 72 degrees isn't one of our choices. We must have done this wrong. You didn't do it wrong. This is where they try to trick you. If you turn it 72 degrees, you're going to get this point will come here. This would come here. this would come here, this would come here, and this would come here. So you'd get it on itself again. But what do you think would happen if you do it 72 more times, 72 more degrees, which is 144? What would happen? Well, this point would have to go here. This point would go here, 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 and here. And that's why it's choice D. Basically, all you're going to do is keep adding 72 until you get to 360. And once you get to 360, then you know you've hit it. And so here for the pentagon, there's our 360, which we don't count. So we know that at 72, I'm going to change colors, that this has rotational symmetry. At 72, 144, 216, and 288. Do not write 360. Say that. Do not write 360. Don't write 360. It doesn't count. All it does is you came right back where you started. It doesn't count. If it was 359.9, it would count. 360 does not count. All right, the end of that question. This one, describe every transformation that maps its figure onto itself. This one's kind of tricky. Some kids are like, oh, I could just take my pen. I could just do this. Nope, because that would end up creating this shape, which would be wrong. So we don't want to do that. Basically, I've done this so many times, I'm just going to tell you. Here, all you're going to do is count boxes. 1, 2. Now count boxes here. 1, 2. So see how this is the middle? So we know that this is a line of symmetry. That line of symmetry is y equals -1. That's the only line of symmetry that has. Same thing here. Even though it says itself and you could technically rotate it, here we couldn't rotate it because it wasn't a regular shape. That rotational symmetry only works if all the sides are the same. But you can have rotational symmetry, or you can have rotational symmetry with a rectangle, but it wouldn't be every 90 degrees. Let's take a look. See how here there's 4? Well, 4 divided by 2 to get the middle would be half. So it'd be 2. So I'm going to put a line right here. So I know that this line would allow me to fold it in half. And that line is y equals 1. Whoa. Oh, no, I was right. Then I'm going to do the same thing with here. I've got 1, 2, 3, 4, 5, 6. 6 divided by 2 gives me 3. So I'm going to go over 3 boxes and draw a line. Notice how I didn't say I'm going up to 1, 3. I'm doing it right in the middle. So this right here. So not only does it have at x equals -2, see this point? That point allows you to change it. Bring on the cell phone. So now we'll use a calculator. So if it was a square piece of paper, I could rotate it 90 degrees and it'd be the same. And I could rotate it 90 more and 90 more. Because this is a rectangle, if I rotate it 90 degrees, it would only look like this. So that wouldn't work. But I could do 90 degrees plus 90 more degrees and get my fidget spinner, my fidget calculator, and that would be the rotation. So then you could also say you could rotate 180 degrees. Guess what? Every rectangle can be rotated 180 degrees. Say that. Every rectangle can be rotated 180 degrees. And that would be a round point, or the center of rotation would be at -2, +1. Yay. Okay. Let's see what else we got. Describe every transformation that maps this figure to itself. A regular hexagon that is centered about the origin that has a vertex of 4, 0. Use a piece of graph paper is all I have to say. I'm not going to graph it, but I'm going to show you. First, we have our rectangle, or hexagon. Hexagon has 6 sides. So I'm just going to draw my 6 sides. Remember, an octagon, like a stop sign, has 8, but a hexagon has 6. Basically speaking, first, it's a regular hexagon. So because of that, we know we could do 360 divided by the number of sides, get 60 degrees. Then we could do 60 times 1 is 60, 60 times 2 is 120, 60 times 3 is 180, 60 times 4 is 240, 60 times 5 is 300. So first things first, we can do rotational symmetry. But the other thing that we can do is we can draw lines. And this is it. You could have a line that goes right through it like this. Since it's centered about the origin, your line would be y equals 0 and x equals 0 because it could go right through it. Then you also could have a line at an angle that goes that way, that goes through those sides. You could have a line that goes through those sides and divides it in half. Now my perfect, it wasn't drawn to scale, of course. Then you also could fold it here, which would make more sense if I drew it perfectly, and here. So if I had to describe this, I would probably say I could use rotational symmetry and rotate at the degrees here, which I'm just going to say whatever these degrees are, that's what you put. Also, you could say you have line symmetry, and the line symmetry would bisect the angles and would bisect the sides. Okay, so basically speaking, if I drew this perfectly, that would bisect, each of these lines would bisect my angles, and the pink lines would bisect the sides. Okay, I think that might be our last one for tonight. Oh, one more. Last one. Okay, so here we go. Which one maps it onto itself? Remember, oftentimes it's a rotation, but not always. If we reflect it against x equals 2, pen tool, well, that means that this point would be here, and this point would be here. So right away, that new blue line doesn't map on top of it, so it can't be choice A. Cross off A. Get rid of this. And then it says y equals 2. Well, if we did y equals 2, this goes down 4, which means this goes down 4. So this would be our new points. And again, this doesn't map onto this. Now, they're actually really polite. The next one says it rotates around 0.22. How convenient of them for them to bisect those lines for you. If you rotate it 90 degrees, it would look something like this. If you rotated it another 180 degrees, it would map on itself. So it is choice C. The reason why it's not choice D is this. This is the reason it's not choice D. If it rotated around this point here, basically what would happen 180 degrees is this would go about like this. I mean, that's not exactly what's happens, but that would be about similar to the rotation of, oh no, that's completely wrong. It would go down like this. And that's how it would be. Okay. So that's why I did a horrible job. That is not even close to right. It would look like this. There you go. So that's why it's choice C. It has to rotate in the middle of the shape, the center of rotation. Pretty much anytime it maps on itself, it's got to be the center of rotation has to be inside the shape. If it maps itself, center rotation is inside the shape. All right. Well, I'm going to head off. Thank you guys for watching and rewatching this. I know you're going to be great. Have a growth mindset. I will talk to you later. Ciao, guys. After school, Monday, April, I don't remember Monday's date, 2-3, April 23rd, angles and proofs worth 35% of the EOC test. Very important day to be there. Bye, guys. It's not letting me click.